Okay, good evening, everyone. Okay, so welcome to our recitation session. Okay, so for today's session, we are going to go through the combinational logic circuit design. All right, and we're going to see how we can use these higher level circuits to solve some problems or some requirements. Okay, yeah, so so I've looked through all the Slido questions as well, so we will address those questions later, okay, towards the end, and then the extra practice question as well. All right, yeah, so I will not go through again all those material from the lecture, okay, because it'll be repetitive. Okay, so along the way, if you have questions, we can discuss, all right, and then see what your doubts are. Okay, so I'll just jump straight into the quiz questions first. All right, so in this first quiz question, we are given this 6% voting circuit that you saw in your lecture slides. And so if you remember from the lecture slides, what this circuit does is it is basically an adder, correct? It's basically an adder where it gives you an output based on the total outcome. Okay, so whenever people add, when people vote, okay, by maybe clicking on some button attached to these pins, all right, you will get the total count, okay, because it's an adder circuit, and that count will be represented in this output here. All right, so since you have 6 inputs, the maximum possible value is 6, so there will be 110. Okay, so that is why you only need 3 bits. Okay, bit 3, bit 2, bit 1. Okay, and the most significant bit is 0. Okay, and we know that, all right, so this count is of course the range is from 000 to 110. Okay, which means from 0 votes all the way to 6 votes. And what we want to do is we want to take this output, which is represented by these 3 bits, okay, and we want to connect it to another circuit where the output of the circuit will be 1, okay, where at least 4 persons have voted. Okay, when at least 4 persons have voted, that means greater than or equal to 4. Okay, so effectively you are doing a comparison, all right, and that already should tell you that we are using a comparator. All right, so from the options here, you can sort of narrow it down and say that it has to be the 2 options with the comparator. Okay, because we are comparing, so we're saying that this output, okay, A, if it is greater than 4, okay, greater than equal to 4, then the output E is equals to 1. All right, so since I want to compare or set it to 1 when it's greater than or equal, so in terms of comparing, we know that we have a greater than, lesser than, or equal. So as long as it is greater than 3, so this is equivalent to saying that A must be greater than 3. Okay, so over here, I can say that the WXYZ must be equal to 3. So 0, 0, 1, 1. Okay, so when my input A is greater than 3, then the output E, which is actually the representing the line A greater than B. Okay, the output will be set. Okay, so that is how you sort of solve this first question here. Okay, so I think yeah, you just need to relate the requirements with the options here. Okay, and then you can sort of narrow it down to this option here. Okay, so the 0 at the 4th input here is basically to add, because this is this circuit is a 4-bit comparator, and since the input from the this circuit here, the output of this circuit is 3-bit. When I connect this to the mystery circuit, which is actually the comparator, then I need to provide a 4-bit input. Okay, but since the input is only 3 bits, okay, it's only 3 bits, what I do is I append a 0 in front. Okay, so that 0 is actually this 0 here. It's just to make the 3-bit value appear as 4 bits to the comparator. Okay, since we're not using the most significant bit. Okay. Any other questions? No. Okay. So I will proceed on to the next question here. So you asked to refer to this circuit diagram. Okay, there's a question. Okay, so there's a question in A. Isn't that 110 become 1100? Okay, so the question is this here, where the question is, when you add the 0, because over here B, when we reference B, we're taking it WXYZ. Okay, that means W is the most significant bit, that is the least significant bit. All right, over here, the if you follow the same convention, then it becomes that the 0 is appended to the back. Okay, appended to the back. Okay, so so there is some I would say ambiguity in this question. All right, because by right, let me look back at the comparator. Yeah. Yeah. So by right, they should both follow the same convention. Okay, but I think here in this question, somehow this 0 is assumed to be the least significant bit, because if I append the 0 at the back, okay, then it doesn't work anymore, correct? Because then that is a value of a value of 12, correct? So it's not going to work. Okay, so I think this one, let me check back. Okay, because by right, I feel it should be the same. All right, that means the ordering should have been the other way around. Okay, so let me check on that. Okay, I get back to you. Okay, for quiz 2, we're supposed to check on this circuit diagram below. Okay, so it asks us to get the most simplified expression. So what we can do is we can label these points first. So we can say W is A dot B. Okay, so this is N. This is OR. So we can call this X as B OR with C, and this is Y, which is C bar. Okay, and ask us to get the expression for F. Okay, ask us to get the expression for F. So to get the expression for F, we can see that this is a exclusive OR operation. So F is effectively W exclusive OR with X. Okay, so exclusive OR is basically means both the inputs must be different and output is a 1. So that can be written as W bar X plus WX bar. All right. So that is a general expression for exclusive OR. Then we can substitute the W and X based on the expression we have here. So this will be A dot B bar and X is B plus C. And this is A dot B and X bar is B plus C bar. Okay, so for these two components, we can do the De Morgan's theorem. So A bar plus B bar and B plus C plus, so this is A dot B and this will be B bar dot C bar. Okay, then I can apply my laws to expand this. So I'll get A bar B plus A bar C plus B bar B plus B bar C, and this is one complete term, so it's A B B bar C. Okay, so whenever you have a literal and with its complement, we know that that term will become 0. Correct, so this will become 0 and this will become 0. So what is left is A bar B plus A bar C plus B bar C. Okay, so at first glance, we may think that we can stop here, all right, but there is one more rule we can apply, which is the consensus rule. Okay, so again, all of this are not easy to remember, all right, so you have to always just look back at your material to know and see for any patterns that you can apply. Okay, so what is the consensus rule? Okay, so let me write the rule first. X dot Y plus X bar dot Z plus Y dot Z is equals to X dot Y plus X bar dot Z. Okay, now if I look at this expression and I relate it back to here, okay, I can rewrite this in a way that I can put the first term as B dot A bar plus B bar dot C plus A bar dot C. Okay, so what happens? Your X is your B, okay, your Y is your A, the Y is your A bar, okay, and your Z is your C. Okay, so with that, I can say that X, Y will be B dot A bar plus X bar Z, which is B bar C. Okay, so again, this step to this step is not so obvious, correct? Because you need to again refer back and see if you can sort of spot this pattern, correct? Spot this pattern in your table, and then only you will see that, okay, I can actually use this rule to simplify to one more step here. Okay, if not, I think if we don't see this, we will probably stop here. Okay, but if you apply all the rules and you apply the consensus rule, finally the most simplified expression would be this. Okay, so that is for this F here, getting the most simplified expression. Okay, so the next step is to calculate the timing. Okay, so we are given that AND and OR gates are 2 nanoseconds, NOT gates 1 nanosecond, XOR gates have 3 nanoseconds. Okay, so basically what you need to do is you need to put the timing parameters back here. So we know that here at this line here, when I look at this first line, I will take 2 nanosecond here, 2 nanosecond here, and 1 nanosecond here. All right, and then when I come here, I will take 3 nanosecond here. Okay, and I'll take another 2 nanosecond here. Okay, so in order for me to compute F, I would have to compute the first stage, which is the AND and the OR gate. So that is 2 nanosecond plus the XOR gate. So F would be 2 plus 3, which will be 5 nanosecond. Okay, for the G, I have two inputs. One input is going to come after 1 nanosecond. The other input is going to come after 2 nanoseconds. So I will take the max time, which is 2, plus the AND gate, which is 2. So that will be 2 plus 2, which is 4 nanoseconds. Okay, so the timings will be 5 and 4. Okay, so I think that should be clear. Okay, so let's look at this. The following circuit implements a function f, a, b, c, d. Okay, so let me maybe read all this a bit bigger. Okay, so we can see that my outputs are 1, 6, and 7. All right, and I have 4 inputs A, B, C, D. Okay, connected this way. So if I were to list out the literals A, B, C, and D, so the first thing we know is B must always be 1. Correct. So B must always be 1 because there only I enable it. So B must be 1. Okay. Now the 3 possible values or the 3 outputs or the min terms that I extract from the decoder are M1, okay, M6, and M7. Okay, so for M1 it will be 0, 0, 1, which means here is 0, 0, and 1. So if I translate that over here, I will get A0, C0, and D1. Okay. Now for here M6, it will be or lines. Okay, so I should not call it M1 now. I'll just call it output 1. Okay, output 1, output 6, and output 7. Okay, so for output 6, it will be 1, 1, 0. So that will be 1, 1, 0. So it will be 1, 1, 0. And for output 7 will be 1, 1, 1. So it will be 1, 1, 1. So 1, 1, 1. So in terms of B is still 1. All right. Then for each of this, I can get the actual min term. All right. The represented by the 4-bit literal. Okay. A, B, C, D. So this will be M5. Okay. This will be M14, and this will be M15. All right. So that's how you get the answer there. M5, M14, and M15. Okay. Okay, so yeah, no questions so far. I'll go on to the next one. Okay, so in the next one, we have a multiplexer. So let me expand this a bit here. Okay, so you're supposed to get the expression for this. All right, so let's see what we have. All right, so we can see that we have three inputs, A, B, and C. So let me write that out first, A, B, and C. All right, now we want the minterms. The minterms basically means those instances where the output G is a 1. Okay, so a minterm is where in a truth table, okay, the outputs are 1. So we want the instances where the output of the system is a 1. Okay, so the first thing we can see is that when B and C are both 1 and 1, we select this line over here. And this line is already 1. Correct? Which means that when B and C are both 1, okay, the output is going to be a 1 regardless of A. So A can be 0 or A can be 1. Okay, so in both of these cases, we can say the output is a 1. Okay, so that is the first thing from the I3. All right. Now we can look at, for example, the next one, I1. Okay, so in I1, for me to select I1, my B and C must be, okay, so I will use a different color. For me to select I1, my B and C must be 0, 1. Okay, my B and C must be 0, 1. Now, when my B and C are 0, 1, A can be 0 or A can be 1. All right. Now, if A is 0, what will be the output? The output will be A plus B, which is 0 plus 0. Okay. And that A plus B, 0 plus 0 will give me a 0, which is not a minterm. All right. So this is actually not a valid input. Whereas if when B and C are 0, 1 and A is 1, then the output is a 1 because the output will be A plus B. Okay. So in this case, the A plus B will give me a 1. So it is a valid input. All right. Now the next one is I2. So in I2 is selected when B and C are 1, 0. Okay. So the output in this case would be the complement of A or A bar. So if A is 0, okay, A is 0, then the output will be a 1. So this is fine, okay, because A bar B equals to 1. But when A is 1, then A bar will be equals to 0. So the output is 0. So this is also not valid. Okay, it's also not valid. So the only combinations where the output is a 1 are this, 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 and this. Okay, which will be M3, M7, M5, and M2. Okay, so that is how we get the answer here. All right, so let me move on. Okay, so that's all the quiz questions. All right, so we'll go through some of the Slido questions before we go on to the extra questions. Okay, so the first question is this 6% voting. All right, so this 6% voting is basically a circuit to count the total number of votes that you have. Okay, it's just summing the numbers. Okay, so what is the application? The application is as it is. That means you can create a system to count the number of inputs being triggered, okay, and generate a count at the end. All right, so that is the objective of the system. All right, so when you say what is the application of it, okay, so it's all depends on what you want to use it for. All right, so in this case, for example, you can have a system where For example, okay, so instead of a voting system, all right, you can think of this as maybe a system to detect faults in some building. All right, so maybe you have a building, all right, that is in a area prone to earthquake. Okay, and if you have maybe a certain number of sensors that are triggered, you want to evacuate the building. So how do you know? How can you build a circuit that can do that? So this is one way, where every input here is actually one sensor reading. And if the sensor is triggered, I will be able to know the final output. And like what we saw in the first question, I can compare this to some value to say that if I hit this particular amount, then I trigger the alarm that people will evacuate the building. Okay, so when we build this kind of circuits, it is the concept or the idea behind what are we trying to solve. Logically, we are trying to do accounting, all right, and then from there we move on to make a decision. Okay, in reality, of course, whether you will actually build the system this way is another question mark. All right, why? Because there are many higher level this kind of combinational circuit blocks. They can do a lot of these things for us. So we already have blocks that can do counting. Okay, they can do comparison, correct, that we have seen. All right, so in some cases we may not actually build a hardware using this approach. Okay, but this is just one way of implementing it. All right, where we have a dedicated hardware to perform this action and give us the output. All right, of course, like I said, nowadays not many people will actually build these kind of systems with just pure hardware. Nowadays, because of software, we will use a embedded system, embedded microcontroller, and interface sensors, interface outputs, and just write the software for it. Okay, but having said that, these are also solutions that still will work equally well. Okay, will still work equally well. Okay, without any software involved, we just do a pure hardware solution. Also, it works. All right, so the application again is dependent on how you want to take this logic and apply it to a different scenario. Okay, so that is probably what I can answer for this. Okay, then there's a question on how you come up with this. So let me go to this question first. How do we come up with this expression here? All right, so these expressions are obtained using the K-map. Okay, and what we do is we translate this to K-map. Okay, so I will just do one example, the D1, to show you. All right, so for D1, you can see that this is a 4 to 2 encoder. So you have 4 inputs. Okay, at any point of time, only one of the inputs will be active, and based on the input that is active, I will provide the encoded value at the output. So I have 2 outputs. So I'm going to draw the K-map. Okay, for the D1, just to demonstrate this only. Okay, so this is for D1. So I have F0, F1, F2, F3, 0, 0, 1. 0. Okay, so over here we can see that 1, 0, 0, 0 is 0. So 1, 0, 0, 0 is 0. 0, 1, 0, 0 is 0. So 0, 1, 0, 0 is 0. Okay, and the 2 ones are 0, 0, 1, 0. So 0, 0, 1, 0 is a 1, and 0, 0, 0, 1, 0, 0, 0, 1 is a 1. Okay, and the rest are all X's. Correct, so I'm going to put all X's here. Okay, and then I can go ahead to do the grouping. So I can do this as one group. So this will give me F3. Okay, and the other group will be this. Okay, this will give me F2. Okay, so that is basically D1. D1 is F2 plus F3. Okay, then you can do the same thing for D0, and then you get the other answer, F2 plus F3. All right, so you can translate it to a K-map, okay, as we have seen before, and just do the grouping to get the simplified expression. Okay, now the next thing is a priority encoder. Okay, so what is a priority encoder? Priority encoder is one where the output generated is based on the highest one. Okay, so I should blue this up a bit. Okay, so if you see down here, when F0 is 1, the output is 0, 0. Okay, when the next bit is 1, F1 is 1, then the output is a 1, 0, 1. Okay, so when it is F0, the output is 0, 0, 0. When it's F1, the output is a 1. Okay, when it is F2, okay, the output is a 2. Okay, 1, 0. Okay, and then when it is F3 is 1, the output is 1, 1. Okay, so you can see that when for a priority encoder, I always look for the highest one. Okay, I always look for the highest one, and I ignore the ones at the lower bits. Okay, ignore the ones at the lower bits. All right, to decide what should be the encoder value. All right. Again, what is the application of priority encoder? All right. So it could always be a case of giving priority to certain signals, certain inputs. Okay. So coming back to the example just now that I talked about. All right. If I go back and say, okay, this is a sensor, okay, monitoring the vibration in the building, I can say that maybe one of the sensor is critical. So the moment that one sensor is triggered, I will straight away sound the alarm. Okay, so that is where a priority encoder can be useful. Okay, so that particular input can be tied to the highest position. And so when the output is at the highest, that means it's 1, 1, all right, then that will immediately trigger the alarm, regardless of the other sensors. Okay, so again, it is a situation where you have multiple inputs, but you want the most important input. Okay, the most important input to decide how the system should behave. All right. In the earlier case, okay, in this case here, we are saying that we have a system where only one input will be active at one time. All right, so that's why we're only interested in these 4 inputs. We do not consider the rest because we do not expect that in the system. Okay, but we may deal with another system where multiple inputs may be active at the same time. All right, and then we want to take the most important one, the highest valued one. Okay, that is where the priority encoder comes in. Okay, so that is sort of the application scenario, okay, of encoder like this. Okay, so there's another question on the multiplexer here. So they say, when we pass inputs to the multiplexer, how do we ensure that we get the same inputs when we demultiplex? All right, so to multiplex and demultiplex, it is about making sure they both have the same selector pins combination. Okay, so if I say that I'm using 2 bits S1, S0, so if I connect them in the same way, okay, so if I say that this is 0, 1, then it's also 0, 1 here. That means whatever is on line 1 goes through, and line 1 will also come out here. All right, that is to ensure that you use the same switch. So when I use the same switch or selector values for both multiplexer and demultiplexer, then that same data that passes through one end will go out the other end. Okay, but if I change things around, okay, then it will be different. Correct, as we will see later in the extra questions. Okay, if the selector pins are not in the same order or have different values, then you may come in at one channel, but you may demultiplex to another channel. All right. So it all again depends on what kind of a system you're trying to build. Okay, what are you trying to do? Okay. Okay, so it is not necessary that you have to always go through or come from one channel and go out the other channel, correct? In some cases, sometimes you want to do it, okay, sometimes you may not, because maybe that channel is now having an issue. Okay, you cannot go by a particular channel, so you need to demultiplex to another channel, and then later you need to do something else later on to recover the data or something like that. Okay, so in a real world scenario, it all depends on where these source and destination lines go to. Okay, and then you can decide how you want to build the system. Okay, so over here, the exercise questions. All right, so what modification should we make to provide and enable input? All right, so what we can do is, if I take this, all right, and I say that I want to create an additional pin, correct? So this is my current input. Okay, and I want to create an additional enable pin. So we know that enable pin, when it is 1, only the whole chip or the whole circuit should work. If it's 0, it should be inactive. Okay, so one easy way is you can just take this, okay, and take this value here and okay, put it through to a AND gate. Okay, before you send it here. Okay, yeah, I mean, okay, so maybe instead of putting it this here, you can put it outside here. Okay, so imagine that is so one is the direct input, which is here. So instead of going direct to the AND gate, okay, so I will break this line. So I'll break this line. Okay, I'll break this line. So what will happen is the current W, okay, and will come here. Okay, and this inverted one will come here, and this will come here. All right, so what will happen? The circuit will still behave as it was as long as enable is 1. Okay, because if enable is 1, then the W goes through as per normal, and it comes to the lower decoder, and the inverted one goes to the upper decoder. Okay, but the moment enable is 0, okay, then both of them okay, wait, sorry, I think this circuit is wrong. Because if it's 0, then this one. Okay, let me redraw this for you. Okay, so you need to add let me see, AND gate here. All right, if I take this input, yeah, so probably you want to add an AND gate here, another AND gate here, and tie them both to a enable pin. Okay, so if the enable is 1, all right, then both of these decoder will behave as before. Okay, if the enable is 0, then both of this enable will be 0. Okay, and both won't work. Okay, so that is how you can sort of add an enable to your decoder. All right, you add AND gates to control the signal that goes to the enable pin of your particular chip. Okay, so that is that one question. Okay, the other one is, how do I construct 4 by 16 decoder using 5 2x4 decoders with enable? Okay, so what you can do is, for this first decoder, you can connect it as A and B. All right, so and this enable could be the main enable signal. All right, and what you do is, when A and B are 0 0, okay, so imagine that now they are both 0 0, I will activate this first portion here. Okay, when A and B are 0. All right, so when A and B are 0, I can take this line and say I want to enable this particular chip. Then based on C and D, I will activate. So when C and D are 0 0, it will be the output 0, output 1, output 2, output 3. All right, now for the next one, when A and B are 0 1, I will come here. All right, and similarly, I activate this line or this decoder. So when C and D are also connected here, what will come out here are these 4 outputs, which is actually 4, 5, 6, and 7. And the same thing. Okay, so when A and B are 1 0, I activate this line or this section. So I connect this to this enable. Okay, so C and D are here. And then I have this 8, 9, 10, 11. And then finally is this. All right, there's the last section here. So this last section, this will be C and D, and that will give me 12, 13, 14, and 15. Okay, so that is how you can sort of use 5 2 to 4 decoders with enable and actually construct a 4 by 16 decoder. Okay. Okay, so these are some of the other questions. What is the difference between canonical sum of product and simplified sum of product? All right, so in a sense, okay, the canonical sum is the expression that you get directly from your truth table. All right, that means when you have your truth table and you express each literal in the or the min term, all right, using all the literals, then that is your canonical sum. And then from there, you can simplify it, all right, either using Boolean algebra or K-map. All right, that is your simplified sum of product. Okay, can we make XOR gate using AND, OR, and NOT? Okay, yes, you can. All right, so if you write back your expression for XOR gate, so we say that Y is A bar B plus A B bar. All right, so what I can do is I can put a double bar. Okay, because a double bar means nothing changes, correct? You invert and invert back. And then from this, I can break that first bar with De Morgan's theorem. So I can say A bar B, put a bar here, dot A B bar, put a bar here, and the original bar is still here. Okay, and then now you see it's all NOT and NAND. All right, it's all not and then. That means I can actually now draw the expression. I'll draw the circuit as A, B. So the first one will be A bar and B, do an AND, and then A and B bar, do an AND, and these two also a NAND. Okay, so that is how you can, of course, this is only one circuit. Okay, I think if you go and sort of Google for it or whatever, you will see that there are many different ways of implementing any gate using AND or NOT or whatever. All right. Yeah. So you can always play around with the logic. All right. And sometimes why we do this is because we do not want to build a circuit. So in the labs, I think you already started with your actual wiring of your IC chips, correct? In the lab. Have you all done that already? Yes, no? Okay. Yeah. So when you do that, you will realize something, correct? You realize that when you buy an IC chip, okay, or when you use IC chip, okay, each IC chip only has that particular type of gate. Correct? That means, for example, I may have 6 AND gates, okay, inside one. Okay, 1, 2, and so on. So I may have or four AND gates or 6 NOT gates or whatever. So each IC chip will only have one type of gate. All right. So if I have a circuit, okay, if I build a circuit, okay, that is, for example, like this, A, B, C with one AND gate, one OR gate, okay, and then one NOT gate. Then to just build this circuit as it is, I would need 3 different IC chips. Correct? I will need 3 different IC chips, which is very inefficient. Okay, as a waste of money. All right. So one of the things that we will try to do is it possible to rewrite my expression using only one type of logic gate, only using AND or only using OR or NAND or something like that. Okay, so by doing that, I may be able to just reduce my entire design into a single IC chip. Okay, a single IC chip instead of using 3 different IC chips. Okay, so those are some of the reasons why we want to do some of this manipulation. All right, even though we already have an expression. Okay. Okay, so is it possible to have infinite loop in circuits? Yeah, in general, okay, I think you're starting that topic now. Or going to start on the idea of sequential circuits. Okay, so a sequential circuit, in a sense, is something that goes on indefinitely. Okay, why? Because it is based on a clocking circuit. Until now, all the circuits we have built, you'll notice that there is no concept of clock. We saw the concept of clock when we were doing the MIPS processor, correct? That when the clock comes in, I trigger the circuit or the whole processor to process the instruction and give me the output. But so far, when we talk about combinational circuit, there is no clock. When I apply the input propagates through, correct? Propagates through all the circuit and generate the output. Okay. So in a situation like this, okay, we call it a combinational circuit. Then the second phase of this, which I think maybe have started or going to start, is a sequential circuit where you have the concept of a clock. So in the concept of a clock, when you design a system or when you want to design a certain behavior, it actually goes on indefinitely because every time you will trigger the next output based on the current input or the current state you're in. Okay, so you will learn or soon you'll be learning about this thing called a finite state machine. All right, so a finite state machine is where you continuously go from one state to another state depending on what you want to do next, and so on. All right, so that is in a sense sort of a loop. Okay, but it is a loop that will just continue. Okay, or is designed to actually run forever because it will always go to the correct state depending on my current state and what is the input that is triggering the system. Okay, so that is the sort of thing that we will see soon. Okay, zero enable decoders. Okay, so I'm not very sure what exactly this question is or what is meant by zero enable. Okay, so when you talk about enable, okay, maybe from what I understand, maybe the question is about active low enable, active high enable. Okay, so if that is the question, basically for any circuit, or for most of these higher level complex circuits or IC chips, you can have a combination of active high and active low enable pins. All right. So even though currently we only see, for example, a single enable pin, all right, we can actually have IC chips that have more than one enable pin, and some may be active high, some may be active low. All right, and you need to make sure all of them are in the active state before the chip works. All right, so I think I'm not very sure. Maybe that is what the person who wrote this question is asking. Okay, that zero enable is active high, active low. So in this example here, for example, you can see that the E is tied to the AND input. Okay, and since it's an AND gate, all right, this is what we call an active high. Okay, so this is an active high enable. So when the enable is 1, then the signal goes through. Okay, so that is basically how you create a active high enable. Active low enable will basically have a bubble in front of each of this AND gate input for the enable. Okay, so okay, so I'll go on to the extra questions part, and after that you can discuss any other things that you have. All right. Okay, so we have a device that basically takes in a 3-bit sign number. It takes in a 3-bit sign number ABC. Its output N is 0 if the value represented by ABC is 0. Okay, or 1 if the value represented by ABC is not 0. Okay, so basically this requirement says that if A, B, C is equals to 0, 0, 0, then N is 0. Okay, so this is the if condition. All right, if this, else we can say that N is equals to 1. All right, so the sort of easiest way to interpret this is to say that N is basically A or with B or with C. All right, so if you try to draw the K-map or whatever, or you put the truth table, you also get the same answer. All right, because if you say ABC and you draw the truth table, only the first entry is where you will get a 0. Okay, all the other entries you will get a 1. Okay, and you will find that the simplified expression will be A, B, or C. So as long as any one input is a 1, the output is going to be a 1. Okay, if not, the output is going to be a 0. Okay, so that is your first part here. Now, second part, they says implement N using the following single 2 to 4 decoder with 0 enable and negated outputs. All right, with no other logic gates and devices. All right, so 0 enable means what? That means this is active low enable. That means when the E is tied to a low, then it's considered, the chip is considered to be in an active state. All right, and the negative outputs means when that particular line is active, then it is a low. Okay, so when a line is active, then it's a low. If not, it is a high. All right, so usually this kind of questions is about trying to think of the hardware that you have, all right, and relate it back to what we want. Okay, so you can see that. Okay, so we're just going to give one possible solution. Okay, if I take any of the input here, let's say I take C and I tie it to enable. Okay, so when C is 0, okay, then we say this chip is active. Correct? When C is 0, we say this chip is active. And let's assume that I try A and B to S1 and S0. Okay. Now, when A and B are both 0 and 0, all right, that will activate line 0. So when you say activate line 0 means line 0 will be 0. Okay, this is the active state. Okay, we satisfy the first condition here. Now, for any other values, okay, when C is 0, any other combination here, 0, 1, 1, 0, 1, 1, okay, what happened? I will activate line 1, line 2, or line 3, and line 0 will go to inactive state. When it's inactive state, is considered 1. Okay, which fulfills the second criteria. Okay, when C is 1, the chip is already inactive because it is not enabled, which means that the output 0 is also in the inactive state, which also satisfies this condition. Okay, so basically all I need to do is take one of the input tied to C, the other input tied to A and B, and my output, okay, would be N will be line 0. Okay, why? Because the only combination where line 0 will be active, okay, in active state is when all three are 0. Okay, in other cases, either the other lines are activated or the whole chip is inactive, which means that line 0 will be a 1. Okay, so that is how you have to think through this implementation here. Okay, so any questions on this? Okay, so if no questions, let me move on to the next part here. Okay, so this question is a bit more tricky. Okay, okay, so this is the one I said where the multiplexer and demultiplexer do not have the same order of inputs. Okay, so on what comes in on the input side on a particular line will go out on the output side at a different line. All right, so if you see down here, we have a comparator, we have a multiplexer, okay, a demultiplexer, and we want to write the SOP expression for P, Q, and R. Okay, P, Q, and R. So let's do it step by step. All right, so for P, okay, now in order for me to write the expression for P, all right, we must have the condition where S1 and S0. Okay, so let me do step by step. So first we are looking at P. Now for P, we can say that S1 and S0 must be equals to 0, 0. Okay, S1 and S0 is equal to 0, 0. That's the first condition. And this implies what? Where S1 and S0 is 0, 0 means, because S1, okay, if you look at this, S1 is tied to, okay, so maybe I should write it. So there's two multiplexer A and B. So for multiplexer A and multiplexer B is different. Okay, for multiplexer A, when X is lesser, okay, so instead of putting X, okay, so we can see the X1 and X0 is tied to AB, Y1, Y0 is tied to CD. So for multiplexer A, when AB is lesser than CD, then S1 is 1. Okay, I should put S1, S0 is equals to 1, 0. Okay, when AB is greater than CD, then S1, S0 is equals to 0 and 1. Okay. On the B multiplexer, it is the other way around. Okay. When AB is smaller than CD, then we say that S1, S0 is equals to 0, 1. Okay, why? Because the S1 over A is mapped to S0 on B. And S0 on A is mapped to S1 on B. Okay, so it is the reverse. Okay, so for both these multiplexers, the S1 and S0 is sort of inverted. Okay, now coming back to this P, we can say that for me to satisfy the condition that S1, S0 equals 0, 0, that means it is not AB less than CD or AB greater than CD. So the only combination is AB, it must be equal to CD, correct? So this implies that AB is equal to CD. Okay, AB is equal to CD. Now, since we are talking about the SOP expression, that means the mean terms, we are only interested in the case where A must be equals to 1. Okay, why A is equals to 1? Because when S1, S0 is equals to 0, 0, that means this A line is the one that is going to go through here and come out here. Okay, so we are only interested in the case where the A is 1. All right, and for A is 1 and AB equals to CD, so it's either 1, 0 or 1, 1. Okay, for AB and CD. Okay, so I'll stop here first. Any questions so far? Anything that I'm not sure? Okay, so let me repeat. So for this first requirement for P, we want the output on line 0. So for me to get the output on line 0, S1, S0 has to be 0. All right, and that implies that from this comparator perspective, that is only possible when X is equals to Y, which means AB equals to CD. Okay, so AB equals to CD, you can have 4 combinations, correct? 0, 0, 0, 1, 1, 0, and 1, 1. But since we are interested in the SOP expression, in the SOP expression, we only look for the case where the output is a 1. So in this case, we only want the case where the A is a 1. Okay, so with that, we can say that the two possible combination where AB equals to CD and A is 1 is 1, 0 or 1, 1. Okay, so that will give me the final expression here that this is A, B bar, C, D bar, or with A, B, C, D. So that is the expression for P. Okay, now let's move on to the next one. Okay, on the Q. Now I want the output on Q. Okay, so let me. Okay, I want the output on Q. Now, if I want the output on Q, we can say that I must activate line 1 on the B multiplexer. That means S1, S0, okay, on the B multiplexer, okay, on the B multiplexer must be equals to 0, 1. All right. Now, this also implies that the S1, S0 on the A multiplexer is going to be equals to 1 0. Okay, so because we know that they are both flipped. Okay, so I want the output Q, but that implies that on the A side, I'm actually going to take the C line. Okay, that's going to pass through and come out on Q. Okay, now how about the relationship between AB and CD? So if we come back and look at the A combination, where A is 1 0, implies that AB is smaller than CD. Okay, AB is smaller than CD. All right, so if I write out the table now, AB and CD. All right, so AB must be smaller than CD, and at the same time, we know that C must be a 1. Okay, why C must be a 1? Because we know that we are interested in the SOP. So since C is the one that is coming through, I want C to be a 1. I want those entries where the C is a 1. Okay, so in terms of the combination, I can say that 0 0 1 0 is where AB is smaller than CD. Okay, 0 1 1 0 is another combination. Okay, 0 0 1 1. Okay, 0 1 1 1 and 1 0 1 1. Okay, so these are all the possible combinations where my AB is smaller than CD. Okay, then from here, I can put this into my truth table. All right. Okay, wait, let me finish this, then I'll answer the question first. Okay, A, B, C, D, 0 0 0 1 1 1 1. So I have these 4 ones and this one. All right, so when I do this grouping and this grouping, okay, the expression I'll get for Q is A bar C plus B bar CD. Okay, now the question, why can't AB equals to CD for 0 0 or 0 1 for P? Okay, so the 0 0, okay, so we have this combination 0 0 0 0 and 0 1 0 1 0 1. Okay, now this also is valid that AB is equals to CD, but in both of these cases, your A is 0. Okay, and we want the SOP expression. Okay, these are all valid entries. Okay, but since your A is 0, okay, we ignore it. All right, because we are writing the SOP expression for P, Q, and R. Okay, so you imagine that right now, okay, what we are having is we are having this very big truth table. Okay, where ABCD is the input, okay, and PQRS is the output. Okay, and what we are saying is what combinations of ABCD will generate the P, Q, and RS for me. Okay, and if I say give me the SOP expression, what do? You look for those cases where the P is a 1, correct, and then you extract out those, form the min terms for that. Correct. So since we know that in this design, okay, for P, it is actually tied to A. Okay, P is actually tied to A, or in a sense tied to A when A is 1, because based on the multiplexer setting, P will actually get the A value. So I'm only interested in those A values that are 1, because then it will show up over here. Because I want the P, when I come up with SOP expression, I only look for those cases where the P is a 1. Okay, so that is Q. So for Q, again, like I said, this is a bit tricky, correct, because of the multiplexer switching. So we just need to be aware of what combination is on the output side, what combination on the input side, all right, and how the comparator is working. All right, so we know that in this Q, S1, S0 is 0, 1 on the B side and 1, 0 on the A side. And for the comparator, that means that AB is smaller than CD. And since the SOP expression is going to take the C value, we only want the case where the C is a 1. And then we come up with these values and then put it in the truth table, and then we get the answer. Okay, and we do the same thing for R. Okay, so let's move on to the next one, which is R. Now for R, which is the third line over here. So let me remove all this. So we're interested in this line 2. So for R, we can say that S1, S0 on the B side has to be equals to 1, 0. Okay, and that means that the S1, S0 on the A side is equals to 0, 1. Okay, and that implies that I'm looking at this particular entry where AB is greater than CD. Okay, and since S1, S0 is 0, 1, okay, on the A side, so 0, 1 means I'm actually taking the B input here and channeling it to the output R. So I'm interested in those cases where the B is a 1. Okay, and AB is greater than CD. Okay, so in terms of the values, I'll get AB, CD, all right, and I want AB to be greater than CD while B is a 1. So 0, 1, 0, 0, okay, then 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0. Okay, and that will give me these 4 entries, and I put them in the truth table. Okay, so I'll get this 1, 1, 1, 1. Okay, and I do my groupings. This, and this. So I'll get my expression as A B C bar plus B C bar D bar plus A. Yeah. So those are your 3 expressions. Okay. So we no need to do for S, right? Because why? Because S, okay, for S, you need a multiplex combination of 1, 1. Okay. And 1, 1 implies that X is smaller than Y and X is bigger than Y, which doesn't make sense. Correct. So that can never happen. Okay. So that can never happen. So there is no expression for S. Okay. So the multiplexer values on both sides can never be 1, 1. Okay, so that sort of brings us to the end. Okay, yeah, of this. Okay, so any questions anybody has you want to ask? Okay, so we are sort of nearing the end of the module already, all right? So like I said, the next part will be on the sequential circuits, all right, use of flip-flops and state machines and so on. And then we will go back to the processor, MIPS processor, to wrap up the pipeline architecture design. And I think there'll be one more topic on the cache design. Yeah, so yeah, a few more things before we wrap it up. Okay, so that's all we have for today. If you have any other questions, you can stay back and ask me. Okay, if you want to discuss anything. If not, I will see you all next week.
Sorry, can I just clarify the last question for the quiz again? Because I feel a bit confused by that.
Okay, give me a minute. This one, is it?
Yes, yes.
They are too pro.
Yeah, so what is the question? Which part? Not sure.
Yeah. Like, so B and C, the values that can be put into is like 0. Wait, why can't we put like 0, 0 inside?
Sorry?
Why can't we put like 0 into B and 0 into C?
Because if I put 0, 0, then I activate line 0, correct? And line 0 is 0. Okay, because we are interested in the min terms. Min terms is where the output is a 1.
So the output is basically the inputs 0, A plus B, A prime, and 1.
Yes.
Then we have to, okay, I think I got it. Okay. Thank you.
Okay.